It's my great pleasure to introduce our tutorial speaker, Shay Moran. Shay is an assistant professor at the Department of Mathematics at the Technion in Israel. He has also received his PhD and even bachelor degrees from the Technion. In contrast to his lack of variety with degrees, he managed to spend his postdoc at 5 institutions: UCSD, Princeton Institute for Advanced Studies, Simons Institute at Berkeley, and Google Brain. In his own words, Shay's main research interest is combinatorial and geometric problems related to machine learning theory. That sounds very broad, and indeed Shay has made significant contributions to a very broad set of beautiful problems, and many of which are at the core of machine learning theory. Among those are his breakthrough results in understanding of compression schemes, private Pac learning, and also sample complexity bounds for Pac learning of VC dimension classes. For his work on this topic, he has received the Best Paper Award at the last Fox in 2020, and the Best Paper Award at Call 2020, as well as the award for outstanding paper in the field of machine learning from the Journal of the ICM. His tutorial today is on the understanding of differentially private machine learning, and he will hopefully give us a taste of the beautiful work he has done in this area. Please give him your warm welcome. Shay, you're muted. We won't be able to.
Yeah, okay, so thank you for this introduction, and thank you even more for inviting me, both you and Katrina. And before we start, let me just ask the audience that to participate as much as you can. So please ask questions. We have a lot of time, and there is no pressure. And also, it will be more enjoyable, I think, if this will be interactive. If this talk will be interactive. So yeah, please ask questions, make remarks. Anything, like don't be shy. And also, I'll really be grateful if you can open your cameras so I can see you. And this will also help me a lot. Thanks, Gergely. Okay, so let's start. So yeah, I guess the meta question or the broad question I will try to address in this talk is, what is the sample complexity of differentially private learning? Namely, how many examples are needed for supervised differentially private learning? So first of all, let's begin with a very quick, intuitive introduction to what is even private machine learning and when is it relevant. So the toy example, which we'll actually use maybe twice in this talk, is the deep neural doctor, right? So imagine that your family doctor approaches you and asks you to share your medical record in order to train this brand new technology, which is called deep neural doctor, and they need as much as medical records they can in order to train it, and it's definitely a very worthy cause. Now, of course, most of us will probably want to help this effort, but if we think about it a little bit more, then we may be afraid that sharing this information might down the road cause some terrible event E, that our personal information will be leaked. Just a few days ago, my WhatsApp account was hacked, and that was really terrible, by the way. So now I'm even more afraid about such events. And okay, so this is an example why we may want to consider privacy issues or the fact that the data may be sensitive when we design learning algorithms. And and this is not the only example. I mean, private sensitive data arises in social networks, right? In the US elections, in the Israeli elections, which will happen next week, people like Political parties have been using this kind of information about us in Facebook. Recommendation systems, right? There was the famous Netflix example. So it's really an issue in modern machine learning that the data can be private, and we need to address this concern. It's not enough just to study sample complexity bound, you know, like in the 80s, that we don't care about privacy or sensitivity. So the main questions that we will try to address and to formalize, and some of them even to answer, is which tasks can be learned while protecting private data, and how much data is needed. So it's clear that you only need more data, right? Like you try to satisfy privacy, you need more data than if you don't care about privacy, but how much more data is needed? So as I said, we will present some partial answers and more open questions, which I hope some of you maybe pick up later and work on. So the outline of the talk is, so the talk will consist of 2 parts, and maybe we'll make a short break between the 2 parts. In the first part, we will discuss the PAC model, the distribution-free model of learning. And in this part, we will present a qualitative, and I stress the word qualitative, equivalence with online learning. This part will also be a little bit technical, so we'll present some of the ideas that go into this equivalence. And also we will ask we will present many open questions that are left in this context. And then the second part of the talk, which will be much shorter, we will try to give a different perspective, or to ask what is the sample complexity of differentially private learning from a different perspective, which is more distribution dependent and maybe more realistic. And in this part, we will mostly just discuss open questions. Okay, so unless there are any questions, let's start with the first part of the talk. So a qualitative characterization of private PAC learning. So the too long didn't read version of the result is that the question that we answer is what can be learned privately in the PAC model? Which concept classes can be learned privately? We will define everything, or at least we will recall the definition soon. So which tasks can be learned while protecting private data? And the answer that we will present is that any task which is online learnable. Right? So if you think about the concept class as a class of experts and you want to online learn them in an adversarial setting, so at least qualitatively, private PAC learning and online learning are equivalent. And the nice thing about it is that, differentially private learning is a relatively young area, maybe 15 years old, while online learning is 50 or even 70 years old. So it's it may advance our understanding of differentially private PAC learning. This connection and although this equivalence may appear surprising when you first see it, it actually builds on very, very strong and deep connections between differential privacy and, in general, computing and adaptive and adversarial setting. So in a sense, this result is just kind of a formal, qualitative, abstract manifestation of many connections that were used and revealed before us between differential privacy and adaptive computation. So, and indeed, there were several works which actually use differentially private algorithms or differentially private technique to get better regret bounds in online learning, and also in the other direction to show that, you know, like the standard online learners are automatically private because they are stable in the right sense. So so really there is this conceptual equivalence between differential privacy, adaptive computation, and stability, which still don't really understand formally how to express it, but it's surely there and it's very useful. Okay, so the formal result we prove is that private Pac learning is equivalent to online learning. So let me now quickly, or not quickly, let me now go through the definitions of all of these words. So what is Pac learning? So this I assume most of you know, so let me go through it rather quickly. So in the Pac model, we assume there is a known class of binary labeled functions, which we call hypotheses or concepts. And the class is known to the learner. There is an unknown distribution on examples. Each example is a pair, a point from X and a label, which is binary. And for simplicity, throughout this talk, I will always assume the realizability assumption that the labels, they come from a function in the class. So the labels are always determined by some function in this known class of functions. So the input to the learning algorithm is a training set, is a sample from drawn independently from this unknown distribution, and it outputs an hypothesis, which may or may not be in the class H. But the goal is to minimize the population loss, which is defined as the probability that the output hypothesis errs on a fresh new example from the same distribution. So this is the algorithmic setting, and a class H, we say that it's Pac learnable if there exists an algorithm that learns it with vanishing population loss, right? So as it sees more examples, the error goes to 0. And the rate at which this error goes to 0 is uniform, right? So no matter what the distribution is or what the target function is, the error will be upper bounded by a function only of n, the expected error, let's say, of the input sample size. Okay, so this is Pac learning. Yeah, so if there are any questions about this, then please ask, but I suppose that probably most of you know it. Okay, so let's now define what does private mean? What is differentially private Pac learning? So to define this, let's go back to the toy example we considered in the beginning of the talk. So if you remember, we have this family doctor, and he asks the patient to share their medical data to train a deep neural doctor. And this patient really wants to help, but he's also afraid that this will cause a terrible event E because of the privacy leakage. And basically, before we formally define differential privacy, let me tell you what differential privacy allows the doctor to, how does it allow the doctor to relax the patient, to reassure the patient. So basically what the doctor can say that since the deep neural doctor is differentially private, then the likelihood of E, of this terrible event that the patient is afraid of, will not be affected by the patient's decision. So whether the patient participates, contributes their data or not, the likelihood of E will remain the same. So they might as well just participate because they want to help to advance medicine. A little bit more formally, soon we will give the complete definition. Differentially private algorithms, they have this property that the likelihood of all events that depend on the output of the algorithm remain roughly the same, almost the same, if we just change a single data point from the input. Okay, so notice already that this is a form of stability, right? The output is stable under small changes to the input data. And I guess technically this is why it's also so related to learnability and to online learning. And okay, so now let's give the formal definition. So we need some notation. So let epsilon and delta be two numbers between 0 and 1, which we call the privacy parameters. So for two real numbers, x and y, we say that x is equal to y up to epsilon delta if these two inequalities hold. X is at most e to the epsilon times y plus delta, and y is at most e to the epsilon times x plus delta. And if we keep in mind that e to the epsilon is roughly 1 plus epsilon, then we see that up to an affine transformation, which is almost the identity, which is close to the identity, these numbers are the same. Right? There exists an affine transformation that maps x to y and vice versa. And this affine transformation is really, really close to identity if we think about epsilon and delta and as small, which we do. And we say that two distributions over some domain are epsilon delta indistinguishable if for every event, the numbers P of the event and Q of the event, the measures assigned to the event by the distributions are equal up to epsilon delta. So this is the only technical component we will need for the definition. So, and usually, let me just note, we'll quantify it later, but we think of epsilon as a small constant and on delta as negligible. So delta is much, much, much smaller than epsilon. I will soon tell you in what sense. Okay, so what is a differentially private algorithm? With this notation, we can define what is a differentially private algorithm. So first of all, it has to be a randomized algorithm. Otherwise, it can only, otherwise it becomes trivial. So we have a randomized algorithm. And we care, or in this context, we talk about algorithms that operate on samples, right? They get samples as input, and they output something, a randomized, they output an hypothesis, A of S. Now, since the algorithm is randomized, we notice for every fixed sample S, A of S is actually not just one hypothesis, but it is a distribution over hypothesis, right? Because it's randomized. The distribution depends on the internal randomness of the algorithm. So differential privacy simply means that, so we say that A is epsilon delta differentially private if for every pair of neighboring samples, right? If we have two samples that disagree on a single example, these two distributions, A of S and A of S prime, are indistinguishable. Okay, so the distribution over output does not change by much if we change a single example in the input. Okay, and if you think about it a little bit, this exactly guarantees what the intuition we gave before, that no matter what event that depends on the output of the algorithm, on the learning procedure, on the we care about, this event will not change by much. It will only change like if we change one example, the probability of the event will only change up to epsilon delta in the way we define. Okay, so, and epsilon, again, you can think about as a constant, let's say 0.1 or 1, whatever. But delta, it is important that it is very small. So it is negligible, as they say in cryptography, but meaning that it's symptotically much smaller than any polynomial in 1 over sample size. Yeah, I will not justify why it's important, but there are excellent blogs online and there are books that discuss why exactly we choose the parameters this way. Okay, so having defined when an algorithm is differentially private, we can define when a class is differentially private, Pac learnable. So as you can probably guess, H is differentially private Pac learnable if it is Pac learnable, and the algorithm that Pac learns it is also differentially private, right? So it satisfies epsilon delta differential privacy for epsilon being a constant and delta being negligible in 1 over the input size. So it's just Pac learnability plus differential privacy. That's it. Okay. So it's a very stable. It's being learned, Pac learned by a very stable learning algorithm. Okay, great. So now let's define the second half of the equivalence. So we know what is private Pac learning. Let's define online learning. So in the online model, we also have a class. We assume a known class of in this context, binary labeled functions. Now, maybe we want to think about them as experts, if you like expert advice. And then the online learning setting proceeds in rounds. And in each round, the learner receives a question, which is an unlabeled example. It's a point xt in x. Then it predicts a label, which is plus or minus 1. Then it receives the true answer, which is also plus minus 1. So y hat is the guess of the learner, and the y is the true answer. And the learner makes a mistake if he guessed wrong, if they guessed wrong. Now the label, the points, the questions, and the labels can be produced by an adversary. So we have no control over that. But the goal is to minimize the regret. So basically what we want is that the total loss number of mistakes made by the algorithm will not exceed by much the number of mistakes made by the best expert or the best function in H. Okay, so that's the goal in online learning. We want to minimize regret, which is we basically want to compete, to design an algorithm that is able to compete with the best expert in class, with the best function in class. And just like in the Pac definition, we say that H is online learnable if there exists an algorithm that achieves sublinear regret, right? So if we proceed for T rounds, then the regret needs to be sublinear in T, which means that the amortized regret, right? If you take the average regret, if you divide by T, then it goes to 0 basically, right? That's the okay, so notice that it's basically a very similar setting like the Pac setting, only that in the Pac setting we have there is no adversary. The sequence comes from an IID distribution, sample from a distribution. Here it's adversarial, and we will mention it later. But there is a very simple combinatorial parameter that captures learnability in this context, just like the VC dimension captures learnability in the Pac setting. But we will discuss it in more detail later. So this is not important for now. Okay, so now, having defined these terms, we can state the main result. So the main result is an accumulation of 2 papers with Noga Alon, Mark Ban, Roy Livni, and Marianne Temaliaris. And basically what it says that for any class H, the following statements are equivalent. H is differentially private Pac learnable, H is online learnable, and H has a finite Littlestone dimension. And the proof, as we will discuss soon, is based on a combinatorial perspective of learnability. And also there is a new notion of algorithmic stability, which may be interesting in its own right. I will discuss it. Are there any questions about the result, about definitions? Please ask.
One question.
Yeah, sorry?
Yeah, so if you define indistinguishability, say in terms of total variation distance instead of epsilon delta indistinguishability. I mean, what changes? Like, so the.
Okay. So basically, like, if you think about it, total variation boils down to the case where epsilon, let's go back, epsilon is 0. Epsilon is 0. If epsilon is 0, then total variation, then it's exactly total variation, right? Delta means that for every two events, and then actually, if delta is at least 1 over sample size, then it becomes kind of trivial to learn. And if it's much smaller than that, then you cannot learn anything. So yeah, it's not very. Actually, the more the first definition of differential privacy was delta equals 0. That was the, and you asked about epsilon 0, which is interesting. But yeah, I don't want to get too much into these technical details. But yeah, basically, but the short answer is that there is no reasonable way to just do the total variation and capture interesting properties.
Thanks.
So Shay.
Yeah.
So Shay, hey, I have a question regarding the role of randomization in online learning. So I suppose you're going to be considering still the realizable case here. So can you say something, is randomization also necessary for getting sublinear regret in this realizable online learning setting or no? Because for private Pac learning, you said that, well, for the definitions to make sense, you need randomization, but what's the case for online learning?
No, so in online learning, so I guess in the realizable case, randomization doesn't really help, right? It may improve by a factor of 2, I guess, and from D to D over 2, the Littlestone-dimension. But in diagnostic, but actually also in diagnostic setting, right? The regret is also, it's always a factor of 2, I guess, but for some reason we don't like 2 opt in online learning. We like opt plus epsilon. Like if
right.
But I guess in this sense, it's always like if you allow for a multiplicative factor, it's a factor of 2. But no, but I will not. I mean, we will not. We will not really talk about online learning. I mean, it will not come up like the role of randomization.
Right, because the conventional wisdom in online learning is that you need to randomize if you want to have sublinear regret, but this is only true in the agnostic setting,
Yeah,
if your comparator is opt.
But even that, it's also only true if you don't, like once you allow 2 opt, if you allow a multiplicative regret, then you can be deterministic, right?
Yes, right. But regret is typically not measured. Again,
yeah, it's typically, but I think, but I think this is more like, and the same also applies to the realizable case, right? I think if you do, I'm not sure actually, but I think if you allow randomization in the realizable case, you can get you can have the mistake bound. The expected mistake bound can be half of the deterministic one. I think so.
Yeah, I don't know if this is supported by lower bands. Do you know anything about that?
I mean, okay, let's take it offline.
Yeah, but this is beside the point. Yeah,
I think this may be true that there is a factor of 2, always a multiplicative factor of 2 between the deterministic and the randomized, also in the realizable setting. But I'm not sure. That's
okay. Very cool. Thank you, Shay.
Sure. Thank you for asking questions. That's very good. Please ask more.
A short.
Okay, so let's go back to. Okay, so we presented the main result, this equivalence.
I think there's another question.
Okay, yeah.
I have a short one, if I may. So you, in your definitions, you always have a general learner. There is no assumption that it has to be proper, right?
Right.
Okay.
Right.
In all of the scenarios.
In all of the scenarios, right.
Okay, and could you get the same equivalence if you make all of them proper?
Yes, it's a newer result than what I'm presenting, but yeah, I will discuss it later. I will present it, but you can get these equivalences also for proper learners. Yeah.
Oh, cool. Thanks.
Okay, so maybe let me just mention a small new application is that, so as I said, one like online learning is an older discipline, and we know many examples of classes that are online learnable, and now automatically all of these examples, we also know that they are privately learnable. So, so you know, this includes like, I don't know, Hamming balls, alpha and subspaces of any vector space. In general, take any system of polynomial equalities. So any class which is definable by polynomial equalities is online learnable and therefore also privately learnable. And let me just make a very quick comment about this. Notice that if I would change equalities to inequalities, then I would still get Pac learnability. Like half spaces are defined by inequalities, right? More generally, any class which is definable by polynomial inequalities has a finite VC dimension. So really the difference between VC and Littlestone is this. In VC, you also allow inequalities, whereas in online Littlestone, you only allow equalities. So this is just a quick comment for maybe for more experts. But yeah, so the point of this slide is just to say that there are many examples of classes that are online learnable, and automatically now we know that these classes are also privately learnable. Now, as I stressed already in the beginning of the talk, the equivalence is really, really qualitative. Okay, so yeah. So what do I mean by that? So basically, what we show is that if we give a lower bound and an upper bound on the sample complexity of private Pac learning in terms of this parameter, Littlestone-dimension, which captures online learnability. But these upper and lower bounds are ridiculously far away from each other, right? So the upper bound we gave initially was exponential in the Littlestone dimension, and the lower bound we gave a year earlier was log star in the Littlestone dimension. Now log star is 5, right? It's a constant for any number. So yeah, so this is. So we can't really say that we understand what is the sample complexity of private Pac learning, right? We can just maybe argue that in some abstract way, we understand what infinite classes are private Pac learnable. And this remains open. So let me just mention our result. It was by Ghazi, Gorovich, Kumar, and Banwansi. It will appear in the next talk, I believe. And they proved our upper bound to polynomial in Littlestone dimension. And they also provided a proper Pac learner, which answers the question that was asked before about can you get equivalence for proper learning. Yeah, so let me, okay, one more comment is that the lower bound is sometimes almost tight. So there are examples like one-dimensional thresholds over a finite domain for which there is an almost matching upper bound up to polynomial factors. So log star to the 1.5 is the best. But the upper bound can potentially be avoided completely, as far as we know. There is no reason to. Yeah, so it could be, so let me state the first conjecture for this talk, that the sample complexity of private Pac learning is polynomial in the VC dimension and log star of the Littlestone dimension. And if you think about it, if this conjecture holds, then it really means that you know, any Pac learnable class, for all we care, right, for all practical purposes, Pac learning can be made private without, so the only, like log star, that's the only effect privacy has. And this conjecture is supported by a line of works for learning geometric concept classes, half spaces, and other. So we don't really have poly VC log star, but we have poly of VC and 2 to the log star, which is instead of 5, it's 32. So it's not so okay. Good. So So unless there are more questions about the main result or this conjecture, I will now move to talk about the proof. I will try to give you some ideas about the proofs, or at least an overview. But first, if there are any questions, I'll be happy to. Nothing? Okay, great. So, as we said, the equivalence is qualitative, and it is based on a combinatorial perspective, so combinatorial characterization of learnability, and a new notion of algorithmic stability. So, you know, combinatorics in machine learning is a very fruitful. There's a very fruitful link between these two areas. So, almost whenever you have like a minimax problem, then there is some combinatorial parameter hiding behind it. And I'm sure most of you know the relationship between Pac learning and the VC dimension. So the VC dimension is a combinatorial parameter assigned to a class, and it exactly captures Pac learnability. There is a similar relationship between online learning and Littlestone-dimension. We will present them, we will discuss them in more detail soon. But there are also plenty of other examples where you have a combinatorial parameter that captures sample complexity or query complexity in machine learning settings. In fact, as I noted before, there is the case in differentially private learning where delta equals 0, so we only have e to the epsilon, and this is called pure differential privacy. And this was actually before, it was the first definition of privacy that was presented. And Vitali actually, and Shao, they have a very, very nice characterization of pure differentially private, pure DP learning, DP Pac learning, in terms of communication complexity. So there is, for every concept class, there is a natural communication problem you can define. And this communication problem can be solved efficiently if and only if this class is differentially private learnable under pure privacy. But this is, okay, what I wanted to say here is that there is a very fruitful link between combinatorics and machine learning, which is also technically very useful when you want to analyze sample complexity. Okay, so let me now define what the Littlestone dimension is. And in order to do that, let us recall the definition of the VC dimension, but I will present it in a strange way. So when is a class of a set of points shattered by a class H? So, you know, the definition is if we see all possible patterns, all possible traces when we restrict the class to these points. Another maybe strange way to phrase it is that if we have this decision tree, where the ith label of the tree is labeled by the variable xi, so every path on the tree, so right, it's the decision tree, so once we consider a function h, so it defines the path on the tree. Depending on what is the value of h of x1, you either go 0 left or right, etc. So if you think about it, x1 to xd is shattered exactly when every path in this tree is reachable by some concept, by some function in h. Okay, so the definition of Littlestone dimension is almost the same, only that now we allow for a richer class of trees. So instead of demanding that every level has exactly the same label, now we allow distinct labels all over the tree. Okay, so the Littlestone dimension is the depth of the deepest complete binary tree, decision tree, which is shattered by h, so that every path is realizable by some function in h. So of course we can only shatter more tree, right? If we allow, in the VC we only consider, oblivious trees, all levels are the same. So with Littlestone dimension, we can only shatter more trees. So the Littlestone dimension can only be larger than the VC dimension because we have more trees to work with, more trees to shatter. And indeed, there are examples like one-dimensional thresholds where the VC dimension is 1, right? You can never see two sign changes, like, but the Littlestone dimension is unbounded. And to see how you can shatter an infinite tree with thresholds, you just consider a binary search process, right? So I'll let you think about it alone. If you think about binary search, exactly, a binary search tree is exactly a tree which is shattered by thresholds, by one-dimensional thresholds. So this tree witnesses that the Littlestone dimension of thresholds is unbounded, but we know that the VC dimension is just 1. Okay. So so now so the fundamental theorem of Pac learning tells us that you know, a class is Pac learnable if and only if it has a finite VC dimension, and moreover we know that the optimal error after seeing n examples is d over n in the realizable case and square root d over n in the agnostic case. So the VC dimension exactly captures the sample complexity of Pac learning. And similarly, we have a similar characterization for online learning. So a class H is online learnable if and only if the Littlestone dimension, which is like an adaptive VC dimension, right? We have adaptive trees, is finite, and we have very similar quantitative bounds on the regret. So it's L in the realizable case, if the labels come from a function in the class, and square root t times L in the agnostic case. Okay, so remember that our goal is to show that differentially private learning is equivalent to online learning. So with this result in hand, we can just prove that differential private learning occurs if and only if we have a finite Littlestone dimension. Okay, so yeah, so there are two directions to this equivalence. The first direction is that if a class is differentially private learnable, then it has a finite Littlestone dimension. This was proven with Noga, Roy, and Mariante. And the other direction is that if the Littlestone dimension is finite, then the class is differentially private learnable. And let me tell you that in the first direction, there is no component of online learning. Like it's really, but the second direction uses online learning tools. But we will discuss this. Okay, so are there any questions about these definitions? And so the next thing will be to briefly discuss this, each of these directions, each of these. Okay, so let's start with proving that private Pac learning implies that the Littlestone dimension is bounded. So what we will actually prove is the contraposition. So we will show that if the Littlestone dimension is unbounded, then the class is not differentially private learnable. And here there is a very interesting phenomenon that we had to deal with. Okay, but before that, yeah, so there are two central ideas. So the first idea is to, instead of considering an arbitrary H, which has an unbounded Littlestone dimension, we will just focus on thresholds. So we will show that in some sense, thresholds are complete for Littlestone classes. And then once we work with thresholds, we can exploit their structure and yeah, there will be an application of Ramsey theorem there. Okay, so let me first first discuss the reduction to thresholds, and there is even an open question here, which I will ask you soon. So how do we capture the fact that it suffices to only consider one-dimensional thresholds? So for this, let's introduce another definition, the threshold dimension. So the threshold dimension of a class H is the maximal number k such that there exist k points x1 up to xk and k functions in the class h1 up to hk such that when you restrict h's to the x's, you get a threshold, right? So hi of xj is 1 if and only if I is at least j, right? So if you look at the incidence metrics of the hypothesis and the points, it's a triangular matrix. It's a threshold. It's like a class of thresholds, right? So and I think one interesting way to think about it is like a combinatorial notion of margin, right? So yeah, I think it's useful also to think about it like that. But you know, we have this geometric margin that, you know, the half spaces are very, very close to the, and this is like a combinatorial abstraction of the notion of margin for half spaces, this threshold dimension. Okay, so again, the threshold dimension is the maximum number k, such that we can find k points, and we get a triangular matrix or submatrix when we look at the incidence matrix, when we project the class to these points. And then there is this beautiful result by Saron Shelach and by Hodges, which tells you that the Littlestone dimension and the threshold dimension are finite together, right? So there is this exponential upper and lower bound between these two quantities. So the Littlestone dimension is at least log of the threshold dimension and at most 2 to the threshold dimension. And here is the open question. So we know that the lower bound is tight, and you can just do like an example where it's tight, it's just thresholds over 1 to n. But the upper bound, we have no idea. And I think it's a nice problem in combinatorics. Now, in terms of machine learning, I think that this result can be interpreted as an extension of the mistake bound versus margin link witnessed by the perceptron, right? So if you think about half spaces, then the threshold dimension exactly corresponds to margin. And this shows you that this link between mistake bound and margin applies more generally in a combinatorial, in an abstract combinatorial context. Okay, but the way we will going to use this result is that if the Littlestone dimension is large, right? So we want to prove that if the Littlestone dimension is unbounded, then it's not differentially private learnable. So we are given a class with very large Littlestone dimension. So we know that there is also a large subclass of thresholds just by this result. And therefore we can just restrict our attention to thresholds. Okay, so this is the first idea in the proof. We don't need to worry about an arbitrary Littlestone class. We know that if the Littlestone is large, then we can identify a subclass, a large subclass of thresholds, and we only focus on thresholds from now on. Okay, so it suffices to show that the class of thresholds, over say the natural numbers, but it doesn't matter, is not privately learnable. Okay, so that's what we're going to do from now on. And let me mention here that for this class of thresholds, it was known that proper private learning is impossible. And this is a result of Mark Boone, Kobi Nissim, Uri Stemmer, and Salil Vadan. And also by Vitalis and Chow characterization of pure privacy, we know that there is also, this class is also not learnable for under pure privacy. Okay. And now we come to the second idea. So we just want to prove now that thresholds cannot be differentially private Pac learnable. How do we do that? And here there is a very interesting challenge. So our goal is to show that every DP algorithm A cannot learn thresholds, right? If you take a differentially private algorithm, that it will fail to learn thresholds on some distribution. So we need to find some hard distribution D for this algorithm A, right? We're given a differentially private algorithm and we need to find a distribution which witnesses that it fails to learn thresholds. Now, typically in machine learning, the way we derive such results is by a minimax approach, by which we construct a single distribution D, which is hard for all algorithms, right? So if you prove a VC dimension lower bound for Pac learning, you just take a distribution which is uniform over a sharded set, or anyway, supported on a sharded set. But it's one distribution that is hard for any algorithm. So, and this actually gives you a stronger statement, right? Because it tells you that even if the algorithm knows the distribution, it will not be able to learn the class. That's what we usually achieve in lower bounds in machine learning. That even if you know the distribution, the marginal distribution, it's uniform over a sharded set, then you can still not learn the class. Now, this approach is infeasible here, right? If the marginal distribution D is known, then thresholds are differentially private learnable. And any VC class is actually. And the reason is because once the distribution is known, you can construct a cover for the class with respect to the distribution. And you basically have a finite class now. And we know that finite classes are differentially private learnable. Okay, so this is a very strange phenomenon that happens here, that you can't really use the minimax in the usual way, in the standard way that we are used to. So we need to tailor D to construct D in a way that really depends on A. So we need to somehow take A and reason about A to define a distribution D, right? We cannot just define a universal distribution that is hard. But you know, how are we going to do that? Like A is an arbitrary learning algorithm, possibly improper. It's just a mapping from samples to functions. Like what? It can be arbitrary, right? All we know that is that it's differentially private, but what does it even mean? It's not clear how to use it. So the high level idea is to apply Ramsey theory and to find a large Ramsey theory with respect to A. So we're going to use A. I will soon tell you what Ramsey theorem is, but we will apply Ramsey theory on an object that comes from A to find a large subset of the domain, and then on which the behavior of A is very, very regular, is very predictable. So A is very structured on this set, and then the hard distribution will just be uniform on X prime. Okay, so by the way, how much time do I have left? I'm not sure.
Let's say about 35 minutes. 35 minutes,
okay, that's good. That's good. So, okay, so let me just recap this part. So again, we cannot use the minimax lower bound approaches in the usual way. We really have to find a hard distribution which is a function of the algorithm A, for which we prove a lower bound against. And we use Ramsey theory to do it. Let me briefly tell you something about Ramsey's theorem. So yeah, so the intuition is that, you know, if you have a very large object, then there is a smaller object in it which has structure. And this is exactly what we want here, right? We are given this arbitrary algorithm and we find some subset on which it's structured, it's predictable, and we can reason about it to get a lower bound. And yeah, and another nice thing about Ramsey theory is that it helps you get really these strange bounds log star in your proofs. So you know, the baby version of Ramsey theorem is that any group of 6 people contains either 3 mutual friends or 3 mutual strangers, right? So if you have a graph on 6 vertices and you color the edges of this complete graph into colors, then there is a monochromatic triangle. And there is a nice story about this that I don't remember all the details. Noga told it to me that a psychologist, I think in Hungary, discovered this result empirically. You know, that any group of 6 people, they and he asked Erdos, like, you know, they maybe, yeah, I don't know the details. You should ask Noga, but it's a really funny story. Okay, so yeah, so more generally, Ramsey's theorem tells us that if we have some ground set T, and we look at the complete hypergraph or on subset of size n, so, and we color them, so every hyper edge, every subset of size n of T, we color with C colors, then we can always find a large monochromatic set. We can find a subset of the vertices, all of its n subsets have the same color. So formally, okay, so this is like a coloring. Here we color triplets with whatever, 3 colors. So what Ramsey's theorem tells us is that if the domain size is large enough, if T is larger than some function of these parameters, then we can always find a monochromatic set of size n. Right, so and we use it as follows. So we take an algorithm. The algorithm is defined on samples of length m, and then we define from it a coloring of all m subsets of the domain. And by Ramsey theorem, we get a monochromatic set, and then we see that the way we define the coloring means that this monochromatic set, on this monochromatic set, the algorithm is very, very regular. In particular, it looks like it's proper, maybe, on this set in some sense. So we start from an improper algorithm, and then we get something which looks like a proper algorithm. Intuitively, it's a... So, okay, so this is just a very rough overview. And the most technical part in the proof, which is also very short, is after the application of Ramsey theorem to actually argue that this is a hard distribution, the uniform distribution on the monochromatic set. Okay, so this was for the first direction. Now let me quickly tell you about the second direction, and then we'll do a quick break, and I'll tell you about the distribution dependent learning, which is very short, don't worry. Okay, so now I want to discuss how you prove that online learnability implies private learnability, right? So we're given a class with a bounded Littlestone dimension. How can we privately Pac learn it? So the proof here has 2 steps. So first we show that if the class has a finite Littlestone dimension, or more precisely, if we have an online learning algorithm for this class, then we can convert this online learning algorithm to something we call a globally stable Pac learner. And then once we have a globally stable Pac learner, then really standard arguments imply a differentially private learner. So really the key step here is to get this globally stable Pac learner. Let me tell you what it is. What does it mean to be globally stable? So it's a property of a learning algorithm, right? So there is no class even if you want. So a learning algorithm A is globally stable if for every distribution D, there exists an hypothesis H that depends only on D, not on the input. And the probability that the algorithm outputs H is not negligible. It's at least some constant. Okay, so it means that there exists a frequent hypothesis for every distribution. There will be some hypothesis which appears rather frequently as an output, right? So and you can think about it as a variant of pseudo-deterministic algorithms in the right. So for those of you who know pseudo-determinism, it's like a variant of pseudo-deterministic algorithms. And then the proposition, this is the main result, this is the main technical result, is that having a finite Littlestone dimension is equivalent to being globally stable Pac learner, and it's also equivalent to differentially private Pac learnability. And the reason we called it globally stable is because differential privacy is like local stability, right? You do a local change to the input and the output doesn't change by much. And global stability is more like the existence of a maxima, right? Of a global maxima. There exists a single point, which is very, very common, which appears frequently. So it's like, you know, this is like about the derivative DP, differential privacy, and this is more about a global maximum or minimum, or I don't know if it's a good analogy, but that was our intuition. Yeah, so as I said, like to get global stability from online learnability from finite Littlestone dimension, this was the main technical part. And the second part, that once you have global stability, you get differentially private Pac learnability is standard. Basically, you apply the globally stable algorithm many times, and you output the most frequent hypothesis. And you know that you will see this frequent hypothesis quite often, and then you can just use histograms to detect it with privacy. Okay, and yeah, the last is what we already discussed. Okay, so this is the last slide of the overview, I think. So how do we get from online learnability, from online learning to global stability? So we have a class of Littlestone dimension D. And what we want is a globally stable learner for age. And as we said, we assume realizability. So we assume that the examples are labeled by a function in the class. So the key idea is that we have an online learner for age. And in the realizable setting, this online learner is guaranteed to make at most D mistakes. This will be the key component, the key property. So let me give you an idea on how to prove a weaker statement. So imagine just for now that we actually have an infinite sequence of examples drawn from the distribution, right? So we have x1 a star of x1, x2, an infinite sequence of examples, unbounded. It goes forever. And now apply this online learner on the sequence. Okay? So the online learner will make at most D mistakes on this infinite sequence, right? In particular, after some point, it will not make any mistake. So it will have the same hypothesis in mind forever after some finite step of time. So it's not only a probably approximately correct learner, but it's eventually exactly learns H star, right? And so you actually get here global stability with frequency 1, right? If you take the infinite sequence, you will always see the same hypothesis in the limit after. So this is the idea. And to make this uniform, so this is a non-uniform global stability, right? In the limit, in some sense. To make it uniform is a bit of a pain. And in particular, it causes an exponential drop in the frequency. Instead of 1, you get like 2 to the minus Littlestone dimension, which is the reason for the exponential sample complexity bound. Okay, so this is the high level idea, and I think this gives a fairly good intuition of why this should be correct, at least. Okay, so now some open questions, and then I'll just present the last the distribution dependent private learning. So yeah, this is the main result, right? This equivalence between differentially private Pac learnability and online learnability. So one interesting research direction is, to go beyond binary classification. So Jun, Kim, and Tewari, they show that for multi-class, you can extend this result that I presented for multi-class classification. And for regression, they only showed one direction, and the converse is still open. Also, you know, this equivalence only holds information theoretically in terms of sample complexity versus regret bounds. You could also ask whether you can get these results algorithmically, which is a very important question. And yeah, also here there are a bunch of forks, but and we have at least one negative result that assuming one-way functions, then there are classes which are privately learnable, even pure in the pure setting, but they are not online learnable. But this is in the non-uniform model. In the uniform model, actually, anyways, I don't want to get into it. But also here, it's still open. For instance, if you can take any online learner and convert it to a private learner, this is open. If any online learner can be automatically converted to a private learner, this is an open question. Also, another nice kind of technical question is boosting privacy. So a corollary to our characterization is that if you get, so you remember that we had this delta, and delta required to be small, like sub-polynomial, right? What actually our result shows you is that if you can get epsilon delta private learnability with delta being 1/n², then you can also get, maybe not efficiently, but you can also get delta being exponentially small in n. Non-efficiently, it's just because the Littlestone dimension must be finite, and then once the Littlestone dimension is finite, the globally stable learner implies the exponential dependence on n. And yeah, can we make this boosting or privacy amplification algorithmic? Like you're given a differentially private algorithm with polynomial delta, sublinear delta. Can you make it exponential? It's exponentially small. Okay, so yeah, here I summarize the open questions. Later, if you want to remember, you can just go back to this slide. Okay, so we're done with the first part, and the second part, as I said, is really short. Now the question is, how much time do I have?
Maybe maximum 20 minutes.
20 minutes, it's more than enough. So
I have a question.
Yeah, please go ahead. Yeah, so we have time.
Sorry, for your upper bound results, can it be phrased as a black box reduction that uses an online learner?
Yes.
And what is the oracle complexity?
Yes, so you can take any online learning algorithm in the mistake bound model, so that it makes at most k mistakes or d mistakes or L, let's call it L, Littlestone dimension. And you can use this algorithm as a black box to produce, I think. Okay, I need to go more carefully over the proof, but I think something like this can be done. And the oracle complexity will be exponential in L, at least for our algorithm. I'm not sure about the new result. I still haven't deciphered it. But at least our algorithm is, we'll call it exponentially in L times.
Okay, thanks.
I think so, but I'm not 100% sure, but yeah, I think so. Okay, any other questions about the?
Can I ask a question?
Of course, yes.
So regarding the question of converting an online learner to a private learner, so do we know the trivial like online to batch conversion probably doesn't work? So
online to batch, I guess, is a way to get a generalization bound for online learning algorithms in a statistical setup.
Right.
So I don't think. So maybe what you're asking is, can you just take the online learner and it's automatically differentially private? You just maybe that's what you're asking, like in the online.
Sort of. I mean, you do online to batch conversion. You basically just like, I don't know, uniformly a random sample one of the hypotheses?
No. It's much more complicated than that. In order to,
no, I mean, but I'm asking, do we know that like provability doesn't work because it sounds quite stable to me?
Yeah, we know that this cannot work.
Oh, okay.
Yeah, for sure. Yes.
Okay, thanks.
Sure. Yeah, thank you. Okay.
I have a question.
Steve, yes, sure.
So the in terms of sample complexity, do you feel like you have the optimal sample complexity for globally stable learning?
No.
This also
same bounds.
Okay, so it's upper and lower bounds still have a gap.
Exactly. Yes. Yeah. Maybe a good comment now would be that so you can have we have many forms of algorithmic stability, right? We have differential privacy, we have this global stability, we have Pac-based stability, we have low mutual information, we have uniform stability. For any pairs of metrics, one on the input space, one on the output space, you can define a stability with respect to these metrics. And for some reason, which is completely mysterious to me, many of these notions of stability are captured by Littlestone dimension. So if you require Pac learning plus some notion of stability, then it only happens when the Littlestone dimension is finite or when the class is online learnable. But in all of these examples that I know, so I know mutual information, I know differential privacy, global stability, and Pac-based scale divergence. So for all of these examples, you would get these strange bounds, like it's between polynomial or even exponential in L and log star in L of L. Right, so the question is, can you Pac learn stably using a stable algorithm? So for many notions of stability, they're all equivalent to online learning, but the quantitative bounds are very, very loose and strange. Okay, so let's, so anyone who lost me completely, now it's a completely new thing, and it's also much less technical, so please join us. Okay. So now I'm going to suggest a distribution-dependent perspective, which maybe is more realistic even. And okay, so let us recall the formal definition of Pac learning. Okay, again in the realizable case. Okay, so this is a little bit technical, but you all saw it once. So H is Pac learnable at rate R if there exists an algorithm. One algorithm, universal algorithm for any distribution, such that for every realizable distribution D, and for every N, the expected loss of the algorithm is at most R. Okay, that's the definition of Pac learning. I omit delta here and I just take expected loss for those of you who worry. And we know also that the optimal rate is the VC dimension over N for Pac learning. But notice that this bound is distribution free, right? The same upper bound of the rate applies uniformly to all distributions, right? So this bound R, it exists and it applies for all realizable distributions simultaneously. And this really focuses on the worst case, right? It's really a worst case definition. And in practice, we have a fixed distribution and we get more and more samples from it. We don't change the distribution as the sample size changes. So maybe it's more realistic to allow some dependence on the distribution. So here is the definition of universal learning. So all we did is we took the previous definition of Pac learning and we added this existential quantifier here. So still we have one algorithm, a single learner. For all distributions, there will be a pair of constants that may depend on the distribution, such that the loss, the error, will be bounded by this big C times R of little c times N. Okay, so we allow for some dependence on the source distribution, on the target distribution, in the form of these two constants. And once you consider this definition for learnability, the landscape changes quite dramatically. So for instance, what was already shown by, I guess, the first theoretical work that showed that was by Schumann's in the 90s. So you can exhibit VC classes for which the Pac rate, the uniform rate, is linear, VC over N. But if you consider this universal definition, where these two constants comes, then any fixed realizable distribution is learnable in an exponential rate, so much, much faster. In fact, it is learnable so fast that you cannot even test what is the error of the hypothesis you output, because you just need right? You learn really, really fast. And this has also been observed in practice already in the 90s for neural networks. That so you see, we only allowed for a little bit of dependence on the distribution in the form of these constants, and we see a much more optimistic landscape of learnability for some problems. Let me also mention that these constants in fixed problems, in concrete problems, they may depend on margin or smoothness. So it's not just abstract constants, like they really allow you to exploit the structure of the distribution to analyze the rate better, if you know anything about the structure. Okay. So in a joint work with Olivier Bousquet, Steve Haneke, who is here, Ramon Van Hendel, and Amir Yudayov, we studied this universal learning setting in the distribution free, in the realizable setting. And we showed that instead of a dichotomy, you have a trichotomy, and then every class H is either learnable in an exponential rate, or linear rate, or arbitrarily slow rates. And let me mention that there are even examples of classes with unbounded VC dimension. So they are not Pac learnable, but they are still learnable in an exponential rate in this, once you allow these constants. And also, unlike the distribution free setting, which is basically where there is only one algorithmic principle, the ERM, right? What you see is what you get, optimization equivalent to learning. Here, there is a much richer algorithmic landscape, which I still don't really understand. But in particular, online learning is really a key component. Maybe Steve will disagree with some of the things I say, but he can protest later. And okay, so basically my point is that once we change the definition a little bit, we get a much more favorable peaked landscape of learnability. And it is also interesting to explore differential private learning in this setting. Right, so we will say that H is differentially private learnable at rate R if there exists a differentially private algorithm. So still, the algorithm has to be differentially private in the same sense, right? So whenever the input size is n, so it is epsilon delta private, with epsilon being a constant and delta negligible in 1 over n. But we only measure the rate, the learning rate, in this universal, using this universal lens. So yeah, so you can ask many questions, right? But so what are the optimal rates? Can you get exponential rates? Is it true that whenever you have an exponential rate, you can also get an exponential rate with differential privacy? Actually, you can, before that, you can even ask whether there is a, okay, I guess I forgot to tell you that if you take the universal definition of learnability, then algorithms such as k-nearest neighbor, they learn all distributions, right? So once you take the universal definition, you can actually learn all distributions. So the no free lunch theorem is not relevant here. The class of all functions is learnable by k-nearest neighbor or by kernels or whatever. Can we prove a similar result here, that there exists a base optimal differentially private algorithm that learns all distribution? So the second question, I think we know the answer. I think the answer is yes, but which is great news, right? Because it tells you that you can learn everything with differential privacy. But it would be more interesting, of course, to really get bounds on the universal rate, like if you can get exponential rates, etc. Okay, I think that's it basically. So let me just. So are there any questions about the universal part?
So I want to understand this, since this constant depends on the distribution, is this some sort of, do you have some sort of characterization? Also, do you also have the other side of this inequality that you will not be able to learn it for a fixed distribution with a better rate? Maybe I'm not fully understanding the definition. It seems that like I mean, especially if that constant may end up depending on exponentially on the dimension, you want to be kind of very careful with treating it as a constant.
Yeah, so I guess, so like this result, which has nothing to do with privacy, is very general, and of course the constant that we get there, we assume nothing about the class, so we just, there is some, again, combinatorial characterization from which you can get these constants once you fix the distribution. But I guess that there are some recent works, which I forget the authors, but I think Francis Bach is at least one of them, and I think they considered like half spaces, learning half spaces with stochastic gradient descent, I believe. And then they show that the constants there, these two constants, they depend on the margin. Okay, so if the margin is large, then you get an exponential rate, and these constants, they're a function of the margin. So like if we go back to this plot, then of course once it's a VC class, we know the distribution free bound is 1 over n. So we can always get worse and worse constants until we touch this blue curve. But once you fix the distribution, then you get these constants, and maybe if the distribution is nice, and here you will really want to use assumptions about the class, about the distribution, like here you will really want to exploit some prior assumptions, then maybe you can also get reasonable bounds on these constants, and or maybe you can really understand how the constants depend on the distribution. So, but this result that I stated here is very general, and of course it's the constants they come from some combinatorial, actually from an online learning procedure they come. Yeah, I'm not sure. Did I answer the?
I was trying to understand if this is like a characterization, that constant characterizes the rate, but I guess it's probably not, because it does indeed.
So this is indeed a characterization, right? So you have like 3 types of classes, and once so either it's learnable at exponential rate. If it's not, then it cannot be learnable faster than linear rate in the universal sense, right? So even if you fix the distribution, you cannot get faster than linear.
But I was saying, like, up to is the constant characterized? That was my question, not the rate. Sort of this dependence on the.
So the constant is a function of the distribution, right? The constant there exists.
Yeah. So is this function? Do we know that it's that the rate, in the end, the error does not. Okay, once you have that constant, you can characterize it up to a constant, a different constant.
Maybe you can take a recursive definition of universal. But okay, basically what I try to say is that I believe that these works, they understand what these constants are in some cases when you have half spaces with margin or some sort of, then you can, like for specific algorithms, you can understand what this, so they universally learn the class, and you can also bound these constants in terms of parameters of the distribution, which like margin, for instance. But of course, you will have to fix the algorithm, and then maybe you can ask, like, for which distributions do you get better constants, etc.
That makes sense. Let's maybe listen to some other questions.
So any other questions about?
It looks like there's a question in the chat.
Okay, chat. Where is the chat? I'm sorry. Here. For some reason, I don't see the chat. There it is behind. Okay, so I don't know the name. It's someone from Turing Institute. No-free-lunch theorem says that there is no best learner overall. Yeah, okay, you're right. I used the no-free-lunch theorem in what I meant is that the lower bound in terms of VC dimension to the sample complexity of Pac learning. Maybe that was a narrow interpretation of the no-free-lunch theorem. I guess you referred to universal consistency of K and N, or am I missing something? Also K and N. Okay. Yes, so indeed, the K-nearest neighbor algorithm is a universal learner, so it learns the class of all functions, and the rate in which it learns it is arbitrarily slow. And yes, so I hope this answers the second question. And then the last question is also K and N has infinite VC dimension. Does the universal learning rate apply even if the VC dimension is infinite? So I'm not sure what it means that K and N has infinite VC dimension, but the second question, does the universal learning rate apply even if the VC dimension is infinite? Then yes. In particular, we have classes that can be learned exponentially fast that have an unbounded VC dimension. And this is Giovanni Cherubin. Thank you, Giovanni. Sure, no problem. Okay. So let's see. Yeah, so just to summarize, so we discussed two learning settings, the distribution free and the distribution dependent. In the distribution free setting, we presented a qualitative equivalence, but it's wide open to find tight bounds. And in the distribution dependent setting, everything is open. So there's still a lot of work to be done in this context. And yeah, I hope that you enjoyed and it was clear, somewhat clear. Thank you.
Shay, can I ask a question?
Sure, Madi, yeah, of course.
Hi. So I have a question about extending this line of work to the intermediate definition of the privacy, like concentrated differential privacy. So for example, by definition of the concentrated differential privacy, do you think can we have a learning algorithm that is private in terms of the concentration differential privacy?
I'm not sure I know what is concentration differential privacy.
So based on the Renyi divergence.
So instead of taking like so you talk about is there a delta or there is no delta? There's just epsilon, and then instead of e to the epsilon, instead of k.
It's just saying that when you run the algorithm on two neighboring data sets, the Renyi divergence between the output distribution is bounded.
Okay, so as I said before, like, so if I understand correctly, you could take the KL divergence, for instance, and then as I said, so I think that if you take KL divergence, then it is indeed captured by the Littlestone dimension. I think this is related to mutual information also and to Pac base.
Yeah.
So yeah, it could be that for any divergence. So basically what you're asking, if you now you change the notion of stability, instead of taking the privacy definition, you take a Renyi divergence. And my guess is that all of them will be characterized in this way. At least we know that for the L1 case, for the KL divergence, I think we know. This is like mutual information.
Yeah. Because this definition also depends on the order of the Renyi divergence. For example, you have the Renyi divergence between rho, and when this parameter goes to infinity, you can recover like this a pure, for example, differential privacy. So for example, my question is in the CDP paper, they show that for some simple like histogram, the sample complexity based on this definition is exactly between the pure and approximate. So this is why I'm asking this question, that do you think that can we achieve some sample complexity using this recent definition that is somewhere between?
Yeah, it's a great question, but as I said, like I really don't know much about this. Like it's completely mysterious. I think we have some examples of definitions of stability that are captured by Littlestone dimension, and you get the same bounds, mutual information, differential privacy. I don't know what the answer will be for arbitrary Renyi divergence. Yeah, there seems to be a rich landscape of algorithmic stability, and like what some are more expressive than other, like approximate privacy is more expressive than pure privacy. Approximate privacy is captured by Littlestone. I don't know, uniform stability is even more expressive because you can learn any VC class. There is an interesting landscape of algorithmic stability that is, and it will be very interesting to characterize it, or at least to understand, because algorithmic stability is also the bread and butter of societal machine learning, right? Of fairness, differential privacy. So if we have a good understanding of these notions of algorithmic stability, then maybe it can be also insightful in this context, yeah. But I don't know. The short answer is I don't know.
Thank you.
Any other questions?
Let me just very quickly comment. So we know there are some lower bounds for mutual information, which imply that that actually it's a little bit closer to pure DP than it is to epsilon delta. So it's concentrated differential privacy is stronger than epsilon delta notion. And I think it is, in terms of characterization, it behaves more similar to pure, although it is not the same as pure. I think it's like potentially exponentially worse than pure, but it's not like log star, and it's not, you don't get the log star type of dependencies, meaning that you might probably, like for thresholds, you maybe would be able to get it away with them like log n, but not log star.
But in terms of qualitative characterization, so like if you take the example from your paper, the projective plane, for instance, and you, so this is a beautiful class.
I think yes. I think maybe so. I don't know if there is a proof that you can get. So we know you can do better with mutual. If you only want mutual information, I think it's also one. This is I think in your paper with some with Raya.
Also, for mutual information, we know that it's characterized by Littlestone dimension.
Yes. So
I mean, I don't know if it's written explicitly anywhere, but
somewhat. Yeah. So I think it's. So what I'm saying is the CDP is likely to behave more similar to mutual information and to pure privacy than it is to epsilon delta.
Okay. Okay. Thanks.
Anyway, if there are no more questions, we are also out of time. So let's all thank Shay for his great tutorial again.
Thank you very much. Thanks for inviting me.
And we'll all be going back to room A, where the next session I think starts in 7 minutes or so.
No. I'm chairing this session. Okay, I have to go.
It's okay. Okay, see you there.
Bye.
Bye.